In our previous lecture, you remember when we ended right here, right? So we wrote out the number go to string action, and then we minimized the action, and then we found our equations of motion. The condition that this was the equation of motion that we found out. Now, when we're trying to solve any given differential equations, we are given some initial conditions, right? So when we're trying to solve the string problem, right, we are given some boundary conditions. Okay, so there are two kinds of boundary conditions. One is called the Dirichlet boundary condition. The Dirichlet boundary condition says that the endpoints are fixed. Okay, so here you have, if x was the solution and the value of x at 1, the first point, and the second point is equal to some, it will be given to some constant, or it can be equal to some c. Okay, so here you have a string. Okay, here you have a string. It starts from this point, and let's say it ends at this point, and this point, these 2 points lie on a plane, and then we have the Dirichlet boundary conditions. Now, depending on this, the dimension of this plane. So here we have a 3-dimensional space, right? So x1, x2, x3, and here the boundary conditions, the points that are required to specify the boundary conditions, these points lie on this plane, and the dimension of this plane is 2 dimensional, right? Because it's a plane, so we'll call it D2, right? So depending on the number of dimensions required, okay, so these strings end on these planes, and depending on these number of dimensions required, it's called a DP brane. Okay, so if we require depending on the strings that we take, if we require 4-dimensional brane, okay, it's going to be called a brane from now on. So if we require a 4-dimensional brane, these strings end on these branes. Okay, these strings start and begin. They begin and end on these branes, and depending on the dimensionality of the brane, which is denoted by P, is going to be called a D2, D3, and D4 brane, and so on. And then we have the Neumann boundary condition. It specifies the value of the derivative of at the endpoint. Okay, so generally this is what the Neumann boundary condition specifies, and in a B to equal to a constant or some 0 itself. Okay, can be either way. So anyway, so this is the Neumann boundary condition. Now we are going to use these boundary conditions, and in addition to the boundary conditions, we're going to use something called as the we're going to use a constraint equation that fixes the parameterization, right? So we said we're going to parameterize in terms of tau and sigma, right? So we spoke about this. We're going to parameterize the string in terms of tau and sigma, and now we're going to do something called as the gauge fixing. So this is called the gauge fixing condition. So it fixes some condition on the parameterization. So this is what it does. Okay, it fixes some condition on the parameterization. So what does the physical meaning of this constraint equation mean? Okay, so this constraint equation, this gauge condition, fixes the strings to be curves at the intersection of the world sheet with the hyperplanes orthogonal to the vector nu x. So what does this mean? So here we have the world sheet, nu x0, x1, and the other coordinates x2, x3, and so on and so forth. Now, what this gauge condition does is it fixes the strings to be curves whose curves that lie at the intersection with this hyperplane. Okay, so the hyperplane is just any plane that has a dimension less than 1 from the ambient space. So here the world sheet dimension, if it is n, the hyperplane's dimension will be n minus 1. Okay, so this is what this gauge condition does. Okay, this is what this constraint equation, the physical meaning of this constraint equation is, this is what it does. So the hyperplane is nothing but n minus 1. So if the world sheet is n, the hyperplane's dimension is n minus 1. So it fixes the strings are curves of intersection between the hyperplane and the world sheet. So here you have the string, this is denoted here AB. Okay, so this is what this gauge condition does, and then it also does another thing. This gauge condition fixes for curves of constant tau. Okay, so for curves of constant tau, we have constant energy. Okay, energy is a constant for curves of constant tau. So this is another thing that this gauge condition ensures. So now with these conditions, constraint equation, and then with our equation of motion, we have the solutions. We have the solution for our string. Okay, so this is what our solution turns out to be from our equation of motion, and the solution to x nu here is nothing but expanded and written out here. So here we see that this is a plane wave solution, right? So here you can see these are nothing but plane wave solutions. So remember, when you talk about plane wave solutions, plane wave solutions are solutions to the harmonic oscillator, right? So when we have plane wave solutions, that opens us out to theoretically to bring in the quantum harmonic oscillator into picture. So this theory can be easily quantized, right? So for events that are needed when we are needed to describe events of creation and annihilation, we use the quantum harmonic oscillator and rewrite it in terms of the creation and the annihilation operators, and we bring it into our theory, right? So here, since we have plane wave solutions, this theory then can be easily quantized. So what are these new quantities that we are seeing here? So this alpha prime that we see here is called the slope parameter sometimes, and it is nothing but the tension with some other constant. So T naught is the tension, so we have some other constants defined along with this. And what is P nu? P nu is the momentum density integrated with respect to the sigma and within the boundary conditions that are specified here. Okay, so this is what it is. So next, what we want to do is we want to write these solutions in terms of the light cone coordinates. Okay, so remember we had defined the light cone coordinates. So we defined in something called x plus, which was x naught x1 divided by square root of 2, and x minus as x naught minus x1 divided by square root of 2, and the other coordinates remain the same, x2, x3, x4, they remain the same. Here the first two coordinates alone we define like this. So you remember these light cone coordinates that we saw in the first video. Now we have to write, we are talking about the light, we want to write the light cone solutions of the equation of motion, but before that we'll impose something called the light cone gauge. So this is an additional condition. So this is an additional condition or a constraint equation that the solutions must obey. So this is called the light cone gauge. Now in this light cone gauge, we have n dot x is equal to x plus and n dot p is equal to p plus. Okay, and what it does is it simplifies x plus such that it is in this light cone gauge, x plus is equal to this quantity and p plus is equal to this quantity, and all our solutions are there, and all the dynamics of the string can be expressed in terms of xi, which is nothing but x2, x3, and going up to xd. These are going to be called your transverse coordinates. So your x0 and x1 was the coordinates we used to define the light cone coordinates. The remaining were the other coordinates, right? It went up to x2, x3, and went up to the dimension of space, whichever dimension of space we are in. So these are going to be called your transverse coordinates, right? So these are going to be called your transverse coordinates. So the light cone gauge, in the light cone gauge, the x plus is expressed in a simple manner like this, which ensures that the dynamics of the string can be expressed only in terms of the transverse coordinates. Now, here we have the dynamics of the string, the solution of the dynamics of the string expressed in terms of the transverse coordinates. So here it's also given in x minus. Here you can see that there is not the solution is the same thing, right? The expansion is the same thing. Just the coefficients, the corresponding coefficients alone, we have replaced for the corresponding x minus, but the expansion is the same thing. That is what we were discussing here. Okay, so all the dynamics of the string can be expressed in terms of the transverse coordinates itself, because we have defined x plus in a simple manner like this, okay, by the light cone gauge fixing. So now just the relationship between these these coefficients of the x minus and the coefficients of the xi, the transverse coordinates. So remember what these coefficients are. We were saying previously that when we were writing out here, these were the coefficients that we were talking about. These coefficients appear in just before, in front of the plane wave solutions, right? So x e to the power minus I, some argument, and e to the power I, some argument is there. So these appear in front of these plane wave solutions as some coefficients. So when we quantize the theory, remember these coefficients are going to become your creation and annihilation operators, right? So they're going to become your creation and annihilation operators. So we are going to there is a relationship between these coefficients for the x minus, the coefficient that we saw here, okay, the coefficient that we saw here, the alpha minus n and alpha in, okay, the coefficient for the transverse coordinate. This is the relationship is given here, and this ln perpendicular, what is denoted by the symbol, is going to be called your transverse Virasoro mode. Okay, so Virasoro mode. And for a particular value of n, where n is equal to 0, it reduces to be this relationship reduces to what is given here. This alpha prime is your slope parameter, just recall. And we are going to define something called m square. We're going to find the mass of the string. This equation comes from your equation for your relativistic energy equation, right? So, and we are working in natural units. Natural units are set h bar c and h bar and c are set to 1, right? Remember, in your natural units, h bar and c, the value of h bar and c is set to 1. So by that we have this equation, and the dot product in terms of your light cone coordinates for p square. So this is nothing but p dot p. P square is nothing but p dot p, right? So this dot product is expanded in light cone coordinates this way. So we have this is the expansion dot product in light cone coordinates, and what we have is the m square. Okay, so the value of m square, when we substitute from here, we get the value of m square. So remember, just see that it is in terms of the coefficients again. Okay. So therefore, in a quantized theory, these coefficients are going to be operators, and therefore m square will be an operator and will be called your mass square operator. will be called the mass square. That's your mass square, and this will be your in a quantized theory, this will be your mass squared operator. So this is about Light-rone solutions for equations of motion of a relativistic string, right? So if you found these lectures useful, do subscribe to our channel and also do let your friends know that there is something like this available.